Thank you for inviting me. So just to say a few words about myself. So I am currently a faculty member here at the University in the computer science faculty. But I actually started my education in physics. I studied in Oxford and did my up to masters. And then I did a bunch of things and kind of drifted towards computer science and machine learning. But at least I have a warm spot for like actual science. So today I'm going to speak about anomaly detection, which I've been working on for the past couple of years. Now I am aware that this is like a fairly diverse audience, and so if there's anything that I'm saying that is unclear, and I'm sure there will be things that will be unclear, so please ask about it. It would be doing me a great favor. And something else is that I do want to make this quite interactive. So even if what you have is not about something which is unclear or is about a comment or general question, please do ask. I am trying to make this interactive, so please do not be shy. Okay, so today we're going to deal with anomaly detection. Anomaly detection is one of those fields where the definition is somewhat fuzzy, so I will give one definition, but we will see that this definition by itself is not necessarily enough to specify what to do. So the objective of anomaly detection is to discover unique, interesting phenomena, and we'll see some examples of what I mean by anomaly detection. So let's bring a couple of use cases. I guess one of the main use cases is actually in industry, where, for example, we would, in something like cybersecurity, we would try to discover if our network is behaving in an unusual way, and if it is behaving in an unusual way, then we might think we're being attacked. In manufacturing, we might want to see if a product that we are manufacturing is somewhat unusual, because this may mean that the quality is not up to our usual standard. But it also has, and probably like the original place where it was useful, is many applications in science. So for example, in medicine, we would, for example, want to look at routine medical scans, compare them to normal scans that we've seen before, and try to identify different anomalous parts of them, because this may mean that we have some unknown disease or something that is beneficial, but something that is unexpected that we would want to see. More generally, anomaly detection has been said to be the key for discovery in science. So I'm just bringing a specific school of thought from the philosophy of science. I guess it was formulated very nicely by Thomas Kuhn in his famous book, The Structure of Scientific Revolutions. And basically his point of view of how discovery happens in science is that we have a dominant paradigm, and then someone discovers an anomaly, something that doesn't quite fit with the existing paradigm, and this causes some sort of confusion, and then we have to come up with this new theory which replaces the existing paradigm, and at some point the new paradigm, in which the anomaly is no longer anomalous because it's already explained, now becomes the dominant paradigm, and we repeat this again and again. So this is that school of thought. Now we don't necessarily have to take this point of view, but at least I think most of us will agree that anomalies were responsible for some important discoveries in science. I think one nice story is the discovery of penicillin, which many of us already know, right? So at least in the anecdotal story, Fleming came back from vacation, and he looked at his petri dish collection, and he found that he found some parts in the petri dish which had mold in them, and the parts that had mold did not have bacteria, and this basically triggered some sort of an anomaly warning. And he looked at it more carefully, and that led to an important discovery, right? But one could come up with these, one can find that this pattern repeats a lot in many scientific discoveries. We find something that is behaving in an unusual way, and this leads us to a discovery. So I guess the main objective here was to say anomaly detection is important, not just for industry, but is also really important for science and for medicine. And so in computer science, we've been, I guess the field has been trying to come up with effective ways of doing anomaly detection for many decades. So let's just formulate this a little bit more precisely. So the task is, we have a collection of samples, and our task is to detect if a new sample is different from those that we've seen before. Now, this isn't the entire formulation, because it needs to be different in a way that we find is semantically interesting. And this is where it becomes difficult. Now, so we first have a training stage. In the training stage, we have a set of normal samples. And then we have an inference stage in which we observe a new sample and we ask whether it is similar to things we've seen before. In that case, we say that it is a normal sample, and if it is different from what we've seen before, then we say that it is an anomalous sample. And so this is a fairly straightforward formulation of what we're trying to do. So one fairly common way of trying to formulate...
So there's no training for non-normal methods?
Right, so generally in the anomaly detection setting that we deal with, there are no examples of anomalies. I will try to give some motivation for that. The motivation is that anomalies are unexpected. If anomalies are expected, then they're no longer, at least in this definition, they're no longer anomalies. There's something else. There are maybe imbalanced binary classification or some other sort of supervised classification task where we have very few examples of one of the classes. But at least in this setting, this would not be considered anomaly detection. One other question we could ask is, okay, that's fine, but at the end of the day, like, we do have some examples of anomalies, right? Like, for example, we are working in some field of science, like particle physics, and have already discovered some anomalous particles, and then now become a part of, the standard model of particle physics. Can we put them as some sort of a training set and train a supervised classifier between the sort of normal particles and these anomalous particles? But the problem is that anomalies can be different in different ways from the anomalies that we've seen, right? So if we did that, we might be really good at discovering anomalies of exactly the same type as we put in our training set. But again, because anomalies are unexpected, we would not find the really unexpected ones, which is really what we want, right? So supervision is kind of a hairy thing in anomaly detection. And I will try to bring in some ways in which we try to incorporate supervision without sort of violating this requirement of not knowing what the anomalies are. So hopefully we'll get to that in the second part of this talk. Okay, so one mathematical way in which we often try to reformulate anomaly detection is as density estimation. And this is very commonly done. So basically the way that we see it is like this. We try to estimate the probability density function of normal data in the feature space in which we represent them. And then at test time, we take a new sample and we estimate its probability density. And if its probability density is high, then we say that this is a common sample, so it is normal. But if the probability density is low, then we would say that this is an uncommon sample, so therefore it is anomalous. Now, there are many issues with this definition of anomalies, but this is the most common way of trying to mathematically perform anomaly detection. And we'll get to some issues with that in the next couple of slides. Okay, but first of all, let's do a brief recap of how we perform density estimation. So there are different approaches for density estimation. One approach is parametric, in which basically we try to fit a function to estimate the probability density of normal data. And this can be as simple as a simple Gaussian distribution, but this can also be far more complex, such as maybe deep flow models, or right now with deep learning, we have some fairly complex ways of estimating the probability density function of data, especially when it's high dimensional, so it becomes more challenging. However, the main caveat is that the main caveat in parametric density estimation, in parametric density estimation, is that the parametric form has to actually fit to our actual data, and at least with very simple parametric forms like the Gaussian distribution, we might not actually be a good fit for the data. Having said that, on a practical note, at least in my experience, it's usually the case that complex density estimators do not actually perform better than simpler ones for anomaly detection. So there's been a lot of work on that, but if you actually look at comparisons, you usually find out that relatively simple density estimators perform as well as the more complex ones, but they're much faster to use, and they have much fewer sort of hyperparameters, which often allow you to cheat. Okay, so that's one way of doing density estimation. The other way of doing density estimation is using non-parametric estimators, and probably the simplest one and the best known one is k-nearest neighbors. K-nearest neighbors by itself doesn't give you probability density, but it's a good proxy for probability density. So let's just try to do a brief recap of that, although I'm sure we know that, but let's recap that. So the way that we perform density estimation using k-nearest neighbors is we take our test sample and we compute the distances between the test sample to every single point, to every single sample in the training set. Now we order these distances and we sum the k nearest distances to this sample point, right? So we compute the distance between our test point and every point in the training set. We order them, we find the k smallest ones, we sum them up, and this is the k nearest neighbor distance. Now the main idea is that the k nearest neighbor distance is indicative of how anomalous a sample is. And the reason is that if the k nearest neighbor distance is large, then we say that the sample is far away from all the samples in the training set, and therefore it is anomalous. Whereas if the k nearest neighbor distance is small, then we say that it is nearby to at least a few examples in the training set, and therefore it is not that uncommon. Now there are ways of roughly mapping between the k nearest neighbor distance and like an actual density, but we don't usually need that for anomaly detection. Sure.
So actually the metric embedding would play a significant role here,
right? Right, and this is one of the main objectives of this talk, right? Where we say that representation is probably the most important aspect of anomaly detection, and there are different ways of trying to make this better. Right.
Are you also going to address the question of the ground truth estimates, or how you evaluate the truth anomaly detection?
So I'm actually not going to address too much in the issue of evaluation metrics. I can actually, Niv is going to talk about the ROC-AUC evaluation metric that we typically use at least in our community, to evaluate anomaly detection. However, I should say that all of the evaluation metrics that I know that are effective in anomaly detection are supervised metrics. So we actually have to know of some anomalies in order to evaluate our method. And this is something that we can do in research, because we can make up some anomalies and then see if we discover them. But in an actual scientific discovery setting in which we don't know of any anomalies, it would be difficult to evaluate it automatically. We would actually need to see the anomalies that we detected and decide by ourselves if they're truly anomalies or not. We'll talk about that a little bit in a few slides.
There are several questions.
Oh, sure, yeah, Pierre? Sure. Please, yeah.
I had experience in anomaly detection KNN, and it worked really, really good. And it was just shot in the dark to try it, and it worked so good that I started thinking why. And it didn't make any sense for me why it worked so good, because in KNN, like if you even use the elbow method to just choose the number of clusters, and in this case I just chose 2 because I assume there's the normal distribution and the anomaly, and or maybe I will have a few more anomalies, and it works so good, and it seems so real to me because KNN is supposed to minimize the distance, and if the anomaly is so little and so rare, it should ignore it. And do you have any explanation why it works so good?
I'm trying to understand your exact setting because I'm trying to understand if you have like a big data set in which there are some normal data and some anomalies, and you don't know which is which, and then you're trying to classify. So because this is not exactly the setting that we deal with here, but I can comment about this. I think the setting that you're mentioning is what we call the fully unsupervised setting, in which we have a data set which contains a lot of normal data and a few anomalies. And basically you have this massive thing. You don't know of any samples that are actually normal, right? You don't know which is which. And in this case, you're trying to separate between the two. So k-nearest neighbors would work in a similar way to this, but if you have too many anomalies, it might fail if they are clustered. So the thing is like this. The anomalies, although the anomalies, we basically make the assumptions that the anomalies are different from each other. And so basically, although there might be a few anomalies in the data set, we would assume that the k-nearest neighbor distance for every single anomaly from the rest of the data set would be quite large. Whereas for normal data, they would be a lot more clustered, and so we would find a nearby normal example. And so the k-nearest neighbor distance for anomalies would be larger than for normal data. However, this is not guaranteed to work, and the reason is that anomalies might actually be clustered, and if they are clustered, then we would actually find nearby anomalies, and in this case, this would actually fail. So there are a couple of ways of trying to deal with it. For example, we could increase k, and so we would need to find many examples which are nearby us, and even if the anomalies are somewhat clustered, we would still require sort of other samples that would be nearby to them, and so this would still be detected. But I should repeat that the setting that we're dealing with here is that we have a training set consisting just of normal data and no anomalies. So we don't actually have the issue that you mentioned. But this is also a really important issue. And usually the methods that we deal with here can be adapted to that setting with slight changes to hyperparameters.
So you did how? I mean, so you transform the problem from the space of samples to the space of distance to the sum of distance or average distance or whatever to the k-nearest neighbor, but I still need to say what is a anomaly in that metric of distance, and we still need some distribution of what I expect in terms of distances.
Okay, so if I understand your question correctly, what you're saying is it's fine that you've now mapped every example to a distance, but this distance by itself doesn't tell you if it's an anomaly or not. This should be a binary problem, right? Anomaly or not anomaly, and you've just given me a number. So finally, we choose some sort of thresholding function, which all the distances above this threshold are considered anomalous, whereas all the samples that have distances, k-nearest neighbor distances, which are smaller than this function, are considered normal. Now, how do we choose this threshold? Generally, our field doesn't really try to choose a threshold, and Nif is actually going to talk about how we evaluate our methods, in which we basically choose all possible thresholds, and then we average over all these thresholds in some way, in terms of how good we are at detecting. But how would you choose this threshold in practice? One good way of choosing this threshold in practice is to reason as to how many false alarms you're willing to get. Because you have the normal data, and basically by choosing the threshold, you can see how many normal examples would still be considered as anomalous under this threshold. And basically you decide how many false alarms you're willing to get, and this is how you can choose your threshold. So if you're willing to accept maybe 1% of false alarms, then you take your normal data or some normal validation set. You take all the distances, you take the top one percentile, and this is your threshold. If you're willing to have 10% false alarms, then you would choose the 10th percentile and so on. Okay, so this is, I guess, the classical way of doing anomaly detection. This is before sort of any hardcore machine learning. And there's several challenges with this paradigm. The first one is that density estimation is hard. This is actually a really difficult problem in statistics, and it's easy if the dimension is low and we have a lot of data, but when we don't have a lot of data and the feature dimensionality is large, density estimation actually becomes challenging, especially when we don't fit too well any parametric assumptions. So this one challenge is a very common challenge in statistics. But the other issue is, I think, a little bit more subtle, and I think a lot less attention is being paid to it. And this is that the representation that we choose must correlate with the task. So this is a little subtle, so let's try to explain this. So let's consider a representation which contains two parts. We name them C and U. Right, so the first part, C, is correlated with the semantic anomalies that we care about. Right, the things that we would truly consider as anomalies and not just somewhat noisy samples. And the other part of the representation, U, is correlated with nuisance attributes. Things that might be different from what we've seen in the training set, but we don't actually care about them. They would not be semantically anomalies. Now let's give one example. So assume there are representations of retinal scan images, and those representations have two parts. The part C basically is correlated with the presence of new diseases, things that we really care about. And the other part of the representation, U, is correlated with the different scanning device that we have, right? Like a specific hardware that we're using to capture these retinal scans. And this is not something that we care about because it doesn't actually say anything about the patient, it's just telling us something about the hospital or the specific device this was taken by. So if we perform density estimation over the entire representation, then if we have a usual value of C but an unusual value of U, then this would be considered an anomaly. But this is not something that we care about. This would not be a semantic anomaly. Right? So density estimation by itself doesn't actually give us interesting anomalies. It might give us statistical outliers, but we don't actually want to find statistical outliers. We want to find semantic anomalies. And so in order to actually find semantic anomalies, we need to choose the correct representation. By correct, I mean a representation which is correlated with the factors that we actually care about and which would be relevant for anomalies. Now, this is obviously not particularly well defined and has a lot to do with our objectives. And this is what makes this task very challenging. Okay, so I would argue that in the general case, it's unclear that sort of classical anomaly detection has the tools to actually overcome these two challenges for two reasons. The first one is that classical features, unless they are extremely well handcrafted, they typically have sort of sparse and non-regular structure, which makes it often quite difficult to perform density estimation on it, especially when it's very high dimensional. And the second challenge is that classical features often contain irrelevant attributes, because we usually, in the features, we basically collect together a lot of different attributes bundled together, and unless we do really good feature engineering, it's going to contain a lot of irrelevant stuff. Okay, and so deep learning comes along and delivers, and basically it's quite promising that we might be able to do it, to use deep learning in order to do better anomaly detection. And so I would say that in the past maybe 6-7 years, the field of anomaly detection has been transformed. But in terms of ideas, the ideas are often sort of repeats of what we had before, just with deep learning techniques. And the main challenge is how can we apply deep learning techniques in the best possible ways, combine them maybe with old sort of old anomaly detection ideas in order to do much better at anomaly detection. Okay, so how can deep learning actually help to do better anomaly detection? So at least from my perspective, there are two main ways in which we can leverage deep learning in order to perform better anomaly detection. The first way is basically to use it as a more powerful function approximator. Basically, it's because it's more powerful than the linear functions that we've used before, it's going to be in some way useful to us, and I'm going to give an example in which we use this ability in order to perform better anomaly detection. The second way is that it's the representations which come out of deep encoders are more semantic, and they would be better at encoding the kind of things that would be correlated with the factors that would make things anomalous. This is going to be the main direction that I'll take here, so I'm going to elaborate on that a lot more. Okay, so just to discuss the first direction a little bit, although I would say this is what most of the techniques did maybe up to a year or two ago. So I'm just going to mention that in 1 or 2 slides, then I'm going to mention the other direction, which I think is the more promising one. So one direction of performing anomaly detection using deep learning techniques is doing out-of-distribution generalization. Let's try to explain what this means. So the idea is like this. We train a deep classifier or an autoencoder on the normal data only. For example, we train some neural network to take in the data, to take in, for example, our image, and basically try to reconstruct the same image, particularly if we put some sort of information bottleneck on this autoencoder to make sure that it's not too easy for it to reconstruct the entire image. And so basically we train that on the normal data. So we train the autoencoder on a large or whatever training set of normal data that we have. And then at test time, we give it new unseen images. And if the autoencoder is able to reconstruct those images, then we say that this image is predicted to be anomalous. Whereas if it is unable to predict those images, if the autoencoder is able to reconstruct those images, then we say that this image is normal. The reasoning is that because the autoencoder was trained on the normal training set, then it might be really good at reconstructing normal data, but when we go out of distribution, then we know that deep learning doesn't necessarily generalize very well out of distribution, and so this is going to be less successful at that. Yes, please.
Do you know that anomalous data didn't infiltrate your training?
So that's a good question. At least, I mean, we often make the assumption that it didn't, but we can not make this assumption, right? We can say that we believe that our training set is mostly normal, but maybe there are just a few anomalies in the training set. And then there are a couple of techniques in order to remove these anomalies. For example, you train, at least you always have to make the assumption that you don't have too many anomalies in the training set. Because if you have many anomalies in the training set, then it's kind of difficult to speak about anomalies if they're very common, right? So we make the assumption, at least, that there are not too many anomalies in the training set. Then one simple technique that I've found to work is that you basically train an anomaly detection on the mixed data set. You train some anomaly detection method on the mixed data set. Then you reapply it on this data. And basically the things that get the worst score, you remove them from the training set and you train again. Although this may sound a naive method, it actually works quite well. Because the anomalies, at least if the anomalies are not too subtle, then they would still be getting the worst anomaly score, even if they are in the training set, unless you're severely overfitting. But if you're not overfitting too much, there's a good chance you'll be able to actually detect these anomalies in the training set, remove them, then train again. But obviously this is not a perfect solution, and you basically want your training set to be as clean as possible. There are ways of trying to mitigate this, but the best thing is just to have a clean data set. Okay. So one of the main issues with this kind of out-of-distribution generalization paradigm is that we're kind of betting against deep learning. We're betting against its ability to generalize out of distribution. And this is sometimes the case, but this is not always the case. Like, for example, here I brought some examples from DALI, right, where we can see that this text-to-image method, DALI is a method which is able to take in a sentence and generate an image. Now we have stable diffusion, which works a little better. And what we can see is that it generalizes quite nicely out of distribution, right? If we ask it to give us a cherry in the shape of an avocado, which it probably never saw before, it's able to generalize quite nicely to chairs like that. So betting against deep learning's ability to generalize is kind of a scary thing to do. So I think that's one of the main reasons why out of distribution generalization methods are typically not the state of the art right now. Okay, so our approach is to use deep learning in order to give us better representations. So what do I mean by better representations? By better representations, I mean that the distances between the representations are correlated with the factors that we find most semantically important. Or if we say this differently, we basically want to find representations in which if we have a large distance between two images or two data points, then we would say that we would consider these two data points to be very different in the semantic factors that we actually care about. And the nice ability of deep encoders is that they typically give us more semantic representations than we would be able to, than the raw data, and often they give us more semantic representations than we would be able to handcraft ourselves. Okay, so obviously not every deep network would give us a representation which is useful for every given task, right? There's an important question of choosing the correct representation encoder for specific tasks. And so this is something that we've looked at quite extensively. And so previously, many of the approaches tried to train representations in a self-supervised way using autoencoders, contrastive methods, or there's a bunch of different methods in order to learn these representation encoders. What we the idea that we had, and we'll show that it actually worked quite nicely, is that if we take generic representation encoders, for example, for images, if we take a deep neural network which was trained on the ImageNet dataset, which is a large dataset consisting of 1,000 different classes of objects, and it's quite diverse, has many different categories. So it basically being able to solve this task means that we have some sort of good semantic understanding of objects in images. And so our approach was to take this encoder, which was trained on a large external dataset and has nothing to do with the actual dataset that we care about, and try to use this encoder to represent the data for anomaly detection. So we performed a couple of experiments to see how well this performs. So the first experiment we call deep nearest neighbors, and the idea is like this. We take this ImageNet pre-trained encoder, and we use it to map each one of the images, both in the training and the test, to basically deep representations, which consist of a couple of thousand of numbers. And now we perform k-nearest neighbors exactly in the same way that we performed before. Let's just consider the alternative. The alternative would have been, for example, to perform k-nearest neighbors on the actual pixels, whereas here we use this representation encoder to map our images to a deep representation, and then we perform k-nearest neighbors on this deep representation. Yes, please.
Without any fine-tuning on your data set or so?
In this experiment, no. In the second experiment, we'll do some fine-tuning. But yeah, right, in this experiment, it's as simple as it gets. You just download this encoder from the internet, you use it to extract the representation, and that is it. And so the results, at least, were quite surprising to us. This simple approach was able to outperform the state of the art. It's only by a couple of percentage points, which is still quite a lot because there have been many thousands of papers on this data set beforehand. But with a little bit more tweaking, this could actually outperform the state of the art by quite a lot. And so this for us was quite interesting because it means that although one could come up with various types of complex methods, it seems as if just taking a really powerful representation without putting too much and taking off-the-shelf density estimators is already able to achieve state-of-the-art performance. So it feels as if putting more emphasis on the representation is likely to be the more promising direction. Okay, now one question that is often asked is, does this actually generalize across data sets? Like at the end of the day, the ImageNet data set is a very specific data set looking at very specific types of objects. Is this going to generalize to my images? So that's a good question, and we wanted to try that ourselves. And we tried that on a bunch of different types of images, including medical images and scientific images like microscopy and aerial images. And in all cases, this achieved significantly better performance than existing than existing anomaly detection approaches, right? So even though this representation is probably not the best one for each one of the data sets, it seems as if it was significantly better than existing ones. Okay. So we wanted to take this a little bit further and try to use, we tried to use it for anomaly segmentation. Now, anomaly segmentation is a related task in which instead of trying to indicate at the image level whether the image is normal or anomalous, we wanted to indicate at the pixel level of whether this pixel is normal or anomalous. And so we basically tried about the same technique. So now we use the deep neural network to extract representations, not for the entire image, but for every pixel in the image. Now I'm actually not going to go too much into the technical details of that because Niv is going to elaborate on that a little bit more, and you're also going to try this out on in an actual STEP collab. So I should just say that we took the images and we extracted a representation, a deep representation for every pixel, and then we performed exactly the same thing, right? We performed k-nearest neighbors for each pixel. So it takes a little bit more time, right? Because there are many more pixels in our data set than there are images. And we use that, again, using k-nearest neighbor scoring to detect anomalies.
So it's, the pixel is an anomaly with respect to all the images, not just, it's not that this is weird for this image.
Yes, if we wanted to do that just for this image,
or for similar images.
well, I mean, effectively,
Context,
I think effectively this is what we're doing, right? Because we are looking. Okay, so I didn't want to get into the technical details, but this is not a technical detail, so I will get into that. The representation that we find for every pixel doesn't just represent the pixel itself, right? Because the pixel is basically just 3 numbers. It's RGB. That doesn't give you too much into the actual pixel, but it is also looking at the context. And the question is how much context around the pixel we want to take. And this is a design choice which lets you find different types of anomalies.
This was another question. So I understand the notion that you look at the pixel and its neighbors and you say whether this is a funny neighborhood. But something that might be reasonable for a chest X-ray might be very anomalous inside the brain, MRI. So there's the context of what kind of the global feature of the image, and then there's the local features of the area around the pixel that might be saved. So that's the question of context.
Sure. So when I mean that we take context, I don't mean we take a 3x3 neighborhood. These deep features can look at very wide context, including pretty much the entire image. So this is actually a design choice that you have. You can and that we actually tried, and it does make a difference in exactly in the way that your intuition goes. If the anomalies that we're looking for have this kind of very wide context, then we would want the pixel-wise representation to also include some component which tells us something about the global context of the entire image. Whereas if we don't actually believe that the anomalies would actually care about the wide context, then, and we would want to be invariant to the type of image that we're looking at, then we would be looking at features which are much more, with much smaller context. For example, recently I spoke to a semiconductor company, and they actually want to look at very fine-grained context. Because the anomalies don't actually matter too much in terms of like the wide context. Whereas the things that you mentioned actually want to look at very wide context. And this is a design choice that you have, and it's actually very easy to I mean, once you know what you're looking for, it's actually quite easy to implement in practice. And in Yv's practical session, you'll actually be able to do it. Please.
Do you calculate KNN over each pixel in the same photo, or do you compare all the pixels in all the training set? When you calculate KNN and look for a comparison.
So I compare the feature of this pixel to all the pixels in all the images in the training set. Now this can be a reasonably large number, and so there are techniques to speed this up. Either using subsampling, or using clustering, or using core sets, which is something that the recent method did. There are ways of speeding this up. Okay, so again, the results of this experiment were also, at least, were also quite surprising to us, positively surprising in terms of like this simple technique was able to outperform much more complex techniques which were tried before, and this is still the state of the art in anomaly segmentation, although our technique has already been followed up by methods that did better things in terms of like this specific hyperparameter choices and so on. So if anyone's interested, actually Niv is going to refer you to the latest work on this, which actually has like the state of the art results. Okay, just to maybe try to contextualize this a little bit more in a medical setting, something that we have looked at is being able to detect, to look at retinal scans and to try to discover parts of the retinal scan which have disease. And so the way that we did this is by basically collecting a set of normal retinal scans of normal healthy patients. And then for the test retinal scan, we extracted features using this generic network, right, which you can download off the web. It knows nothing about medicine. Definitely didn't go to medical school. And we use that to extract features for every single pixel in every single image. Then we use that then we use the k-nearest neighbor technique at the pixel level, and this gives us the state-of-the-art result. The previous approach that we mentioned would take the entire image, pass it through this feature extractor, get an image level representation, and then compare the image level representation to all the previous normal images that we have seen in training. Now, in practice, in order to detect medical diseases, we found that the pixel level representation was much better at detecting retinal disease. This maybe shouldn't really surprise us, and the reason is that the anomalies in the retina, at least initially, are quite local. And so in order to detect these anomalies, you actually want to see if there is a locally anomalous region. After all, the entire retina might not look particularly anomalous, but maybe some specific parts of it might be starting to deform, and so we'd be able to detect these diseases. So here you can see some examples of the anomaly segmentation that we performed on the retina, right? You can see that it was able to detect the disease part of the retina. And the nice thing is that this was not actually trained on any retinal scans that had diseases. It was just trained on healthy retinal scans, and it could take a new retinal scan, and it could then indicate, one, whether it had a disease or not. And the second thing is that it could actually pinpoint to the exact pixels in which it considered to be anomalous. That's not quite the same thing as saying that these pixels indicate some disease. It just indicates that they're anomalous. But at least the physicians that we work with, they, at least in their estimation, this indicated pixels which were actually indicative of diseased regions. Yes, please.
How standardized are the image supposed to be in this method? For example, if you have a slide shift.
Slide shift is fine. We would not be. So we are reasonably invariant to sort of small shifts of the images. We don't need precise registration or not necessarily even color photometric registration. But at the end of the day, you know, if it's an image from a completely different imaging mechanism or something like that, then we are very unlikely to work on that. So, you know, it's somewhere in the middle. We're reasonably invariant, but it's not perfectly invariant. Yes, please.
What about comparing this pixel representation KNN to like a small batch reconstruction test? Because you could, instead of reconstruction the whole picture, do it for local places, and then find anomalies that error in reconstruction.
So I'm trying to understand the strategy that you're suggesting. There's the k-nearest neighbor method, which isn't necessarily trying to reconstruct things, right? It's just trying to find similar things. And then the other thing that you're suggesting is to use an autoencoder, maybe?
For a batch inside a picture, and if you're bad at reconstructing it, it might be an anomaly, but it's a local anomaly inside the picture. Then you can generalize for this exact task. And I wonder if you compared it.
So, did we compare the k-nearest sort of retrieval-based approaches with autoencoding, reconstruction-based approaches? So, yeah, I mean, these methods, some of them used autoencoders. And so if we take a look at these numerical results, we can see that it significantly outperforms these approaches. I would say, informally, from my experience, I haven't really found autoencoders to work better than retrieval methods in nearly every example that I saw. Retrieval methods, that, in my experience, if you have good representations, typically work much better than autoencoding. There's one case which I suspect that autoencoding, like one specific data set that I found the autoencoding to work better, but beyond that, every time that I tried the two approaches, retrieval methods work better. But this is an informal statement. This is just an observation. Yes, please.
Just a kind of a comment. So we had a paper just in NeurIPS that showed theoretically that something like a UNet performs a Euler discretization of a wavelet basis function. And so what that means is that you might find that rather than looking for anomalies at the deepest level, which are the lowest resolution, or at the pixel level, which is the highest resolution, at intermediate levels, you can show that you get Haar-like wavelet decompressions. So it might be that your anomalies show up at a space frequency resolution within intermediate layers of your neural net.
That's very interesting. First of all, I would be very interested in seeing the paper. But second of all, I think that what we are doing is does relate to what you're saying in terms of like the representation that we choose is actually a concatenation of representations from the different from different levels inside the neural network. So we are already looking at the different hierarchy. And so I think we are also looking at the same thing, right? We are also looking both at the lowest level to try to find these fine-grained anomalies, but also looking at the coarse level. So that's, I guess UNets are also doing that, right? In terms of like, they are looking at
we
what the
weren't-
resolution.
This wasn't looking at anomaly detection at all. It was just trying to get a kind of a mathematical description of what UNets and these compression algorithms look like, and it turns out that it's really interesting because they're actually performing wavelet-like compressions mathematically. That's what they're doing
That's very interesting.
at the different rates.
Thank you. Okay, so this was just my anecdote of how we can apply the things that we've mentioned here to some medical imaging problem. But we've tried that on a lot of different types of problems, and they work in just about the same way. If you take strong, if you take sort of strong off-the-shelf representations, they work quite well on these tasks. And it really depends on what sort of anomalies you're looking at. If you're looking for anomalies which are global, then you want to take an image level representation. And if you're looking at anomalies which do care about the global context but are in essence sort of quite local anomalies, then you want to look at pixel level representations. And then maybe if you have a lot of pixels which have anomalies in them, then you can, or maybe just one pixel which has an anomaly, this is a threshold that you can choose, then you can indicate that the whole image is anomalous. Right? So these are two techniques that one could take. Okay. Another observation is that we found that once we extend the set of tasks that we looked at, then we found that the best representation is not always a deep learning representation, right? Generally in images and text and audio, you find that deep learning works exceedingly well, but once you go further away from these modalities in which deep learning people like working in, then you find that the best representation is not necessarily the deep neural network. So I'll just give a few cases in which we did that. So one case is time series. Well, I really don't have time to go into it, but we found that a much simpler sort of histogram-based representation is performed better than the state-of-the-art for anomaly detection using these kind of k-nearest neighbor methods than the latest deep learning representations. So time series is one of these fields, I think, where one should be careful whether they want to use deep learning or more classical techniques. I think the jury is kind of out in terms of like deep learning in time series. The second place where we again found that classical descriptors performed better than deep learning ones was in 3D point clouds. So there's been a huge amount of work on deep learning for point clouds and in classification and so on. They've shown extremely good results. Specifically in anomaly detection, we've found that classical descriptors, specifically we use something which is called FBFH, but the precise naming is less important. Basically the main idea is that there's been a huge amount of work on descriptors for point clouds, and we've found that classical descriptors actually perform better than the latest deep learning ones for point clouds. The final one is for tabular data, which is quite common, I think, in many of the fields that I think people in the audience are working in, which basically consists just of sets of categories and numbers, and the fields are not necessarily ordered in any important ways. There's not necessarily known symmetries between them and so on. And in that case, we've found that typically there's no representation that's a priori better than just taking the raw data and doing k-nearest neighbors on it. So I think for us this was maybe the most disappointing result. If you have a tabular data set and you know nothing about this data set, then if I had to bet, I would just do k-nearest neighbors and would not try to learn any representations on it. We've tried that on quite extensive evaluations on many tabular data sets, and we've found that this trivial approach is as good as anything else that we have seen. So the main message to take from this slide is use deep learning where it helps, but you don't have to use it everywhere. Okay, so the story so far. Anomaly detection requires a representation such that the probability density function of the normal data is easy to estimate. and that there's a smaller overlap between the normal and anomalous data. So basically, that the feature descriptor is discriminative enough so that normal and anomalous data are basically well separated. And this is the requirement that we have from our representations. And this in the general case, for any given data set, we may not know a representation, which we do it without supervision, because we don't know what the anomalies look like. And so for every given representation, we can just define anomalies that look exactly the same as normal data. But I think the more positive message is that in many useful settings, we can use off-the-shelf representations, and they would have these properties. They would first be quite easy to estimate, and two, they would be quite discriminative between normal and anomalous data. So at least for images, for example, if you take off-the-shelf representations, then for maybe moderate difficulty tasks, then this might work reasonably well. But we'll see in the next part of the talk that there are many cases in which this is insufficient. Okay, so in the remaining half an hour, I wanted to talk about the limitations of existing anomaly detection approaches and the desiderata for what we actually want in anomaly detection methods. So there are 4 desiderata that I formulated. The first one is that anomaly detection methods should be able to use all the available data. So here we've just shown 2 different settings. One, we use some sort of self-supervision on our normal training set. We use that to learn a representation, and then we do KNN on that or something like this. The other approach that we proposed is to take an off-the-shelf representation and to use it in order to perform anomaly detection. But ideally, we would want to be able to use all available data, both our training data, which consists just of normal examples, maybe a few anomalies, but all the available data resources which are outside of our training set. Use the whole of Wikipedia, the whole of every scientific article, every data set, everything like that. Right? We would want to incorporate all this knowledge in order to detect anomalies, because at the end of the day, the scientist is also doing that. The second desideratum is that the anomaly detection methods should be interpretable. Now, I'll try to explain why I think interpretability is more important in anomaly detection than in, for example, supervised classification, where it's important, but I think not as important. The third desideratum is that anomaly detection methods should be able to use guidance from the researcher, from the operator, in order to guide which anomalies are more interesting than others. And finally, they should be able to extend to all data modalities, because generally, I think most anomaly detection research, at least in machine learning conferences, is on images and a little bit of time series. But in science, there are so many other data modalities, and these techniques should really extend to these data modalities. So I wanted to talk about some recent work that we performed to at least to try to make some headway in each one of these desiderata, but obviously we've only made small steps so far. So the first desideratum is being able to combine both external and internal data, right? And we try to give some motivation for that, right? We have our training data, which consists just of normal data, so we want to be able to use that. And additionally, we want to use all the other available training resources, every data set on the internet, every scientific paper, everything like that. How can we do both? So I don't have the answer to that question, but I have the answer to maybe a slightly smaller question, which is assuming that we have a pre-trained representation encoder, for example, something which is trained on the ImageNet dataset, and we also have our normal training data. How can we use both in order to get a better representation? So this is an approach which we call PANDA, and it's by Rice, Cohen, Bergman, and I helped a bit too. And the idea is like this. We first get off the shelf or from some other method, we get a pre-trained representation. Then we do a little bit of fine-tuning of this representation on our normal training data. And then we use this fine-tuned representation, again, with k-nearest neighbors for anomaly detection. So there are actually some slightly subtle issues with that, which I wanted to show here. So how do we actually fine-tune an existing representation on the normal training data? So I think some of us are familiar with transfer learning of deep representation, in which we take a pre-trained neural network, and maybe we stick another linear classifier on top of it, and we train the whole thing together on our smaller training set, and this gives us a slightly better feature representation than we started out with. The problem in anomaly detection is that in the training set, we only have normal data, we have no anomalies. So we don't actually have any so supervised training criteria don't actually help us, because generally in supervised learning, we try to learn a representation which makes it easier to separate between normal and anomalous data. Between class 1 and class 2. But here, we only have class 1, we don't have class 2. Class 2 are the anomalies, but we've never seen any. So we can't train a simple binary classifier and use this binary classifier in order to improve our representation. So instead, people have devised other types of training criteria. One fairly common one is called the compactness loss, in which basically you can see the loss over here. Basically what we are trying to do is we try to make the representations of all the normal data to lie in as a compact region as possible, which mathematically means that we would want for every normal training point, we would want its representation to be as close to the center, to some center point, as possible. So they should lie in a compact unit ball. So this is called the compactness loss. Specifically here, this was used by Wolf et al. This technique is called deep SVD, but there is one essential challenge in that, using this compactness loss, which is that it has a trivial solution. The best solution is obviously to have everything mapped exactly to the center without even looking at the image itself, right? So without looking at the image itself, we just map everything to the center point, and this optimizes this compactness criterion, but it doesn't actually help us to do anomaly detection because both normal data and anomalous data are both mapped to the same point. So this is completely useless for discriminating between normal and anomalous data. And so there have been many approaches trying to mitigate this issue. And we took maybe a slightly different approach. Our approach was, instead of, we call this issue catastrophic collapse, because everything collapses to the center. And so we took a slightly different approach, I think, to what most of the literature did. Our idea was to say, collapse indeed happens, but maybe we shouldn't be too afraid of this collapse. And the reason is that this collapse might happen at infinity. If we train our network for an infinite number of iterations, then indeed everything is actually going to collapse to the center. But what happens before infinity, right? Because infinity is in a long time. And so if we take a look at what actually happens during training, let's take a look at the graph on the left-hand side. We can see the average distance to the center of an average normal point and an average anomalous point. And we can see, first of all, that the representation is initially quite good, because the average distance to the center of a normal point is significantly smaller than the distance to the center of an anomalous point. So the initial representation is already quite good. This was already shown in the first experiments. Now, if we continue fine-tuning this network using the compactness criterion, basically trying to make the normal data as compact as possible, then what we see is that indeed both normal data and anomalous data get closer to the center. But more interestingly, normal data get closer to the center at a faster rate than anomalous data, at least initially. And so what we find is that the collapse indeed happens, but we shouldn't be too afraid of it, because normal data initially collapse to the center faster than anomalous data. And so this fine-tuning indeed improves our discriminative ability. However, we can see that as training progresses, this trend reverses. And at this point, anomalous data gets closer to the center at a faster rate than normal data. So we become less discriminative. This can actually be seen here. Here we can see the ratio between normal data and anomalous, the distance of normal data to the center and the distance of anomalous data to the center. And we can see that this ratio initially increases. So normal data get closer to the center than anomalous data. And then after maybe about 15 training epochs or something like that, then the trend reverses, anomalous data get closer to the center on relative terms than normal data. So the main thing is not to be afraid of this catastrophic collapse, but basically to stop. Basically, we want to stop at the correct time where we enjoy the benefits of the early fast collapse of normal data, and stop before anomalous data, before the trend reverses. So how do we know where to stop? So that's a good question. We tried various techniques, you can see them in the paper, but I think in practice, I would suggest what we found in practice is that using a constant number, there's basically a magic number for sort of a constant number of iterations. Well, if you stop at this number of iterations, then this is not a bad bet of being the optimal point. And this sort of generalized between different data sets and between different data sets and different modalities and so on. This is probably specific to the specific network that you are using. But what we found is that collapse usually happens at the same time for a lot of different data sets. We don't have a good theoretical reason for why this is, but we found this experimentally. Okay, so the main message here is we can use the compactness criterion to fine-tune our pre-trained feature encoder, but we have to stop at the correct time. We don't know exactly when the correct time is, but we have a good guess. It usually happens at the same time for a lot of different data sets. In terms of how this improves results, so we can see the simple baseline is the experiment number 1 that we've shown before, and we can see that this new method, Panda, was able to significantly improve on that. So taking the off-the-shelf representation is a good start, but using both sort of the external data resources and the actual normal training data set that we care about, and combining them together does yield better results than using each one of them individually. Now, obviously, the future directions would be to encode as much external information as possible into our representation, and this is something that we are working on. Okay. Something else that we found, we think is highly important for anomaly detection is interpretability. Now, I'm sure you've heard a lot about interpretability, but I would want to argue that this is more important here than in other parts of machine learning. I think the reason is that in supervised learning, we had an early indication from the operator, from the researcher, as to what they want to see in each class, right? We know that these images should be these images are healthy and these images are sick, and we have some examples of each category, and so we have, at least we indicated to our machine learning algorithm what sort of data we want to see in each class. The problem in anomaly detection is that we never actually specified what anomalies look like. And so it really depends on the computer's representation to decide what they consider to be anomalous, because we actually had no indication from the user in terms of what anomalies they want to see. So we train the state-of-the-art method to perform anomaly detection, and we get a bunch of samples that are indicated as anomalous. Now this is good, but we have no idea if this is good or not. So we see an image that was indicated to be the most anomalous. we take a look at it and we have no idea why it thinks this is anomalous. Or for example, in particle physics, right, we see all types of trajectories, and the computer for some reason indicates a specific trajectory to be possibly anomalous. We take a look at this trajectory. We have no idea why the computer thought it was anomalous, because we don't know what anomalies even look like, and we have no expectation that the computer really knows what the anomalies look like. So we don't really know how to evaluate it. And at this point, we probably give up and we do something else. Right, now let's think about the alternative. The computer would tell us this image is anomalous, but the reason why this image is anomalous is that these couple of features had unusual values. Now this is already something to go on, right? So the main idea here is that in anomaly detection, because the anomalies are not well specified, and they're not even specified at all, we need to have some reasoning from the computer in order to at least have the means to decide whether it's finding good anomalies or not. And this is not quite the same thing as in supervised classification, where interpretability is obviously important, but maybe not as important. So again, we don't necessarily have all the answers to that, but we've done work on a specific task of interpretability in video anomaly detection. But I think the main techniques can actually generalize to any other anomaly detection task that we deal with. And the idea was like this. In academic video anomaly detection datasets, the anomalies are typically separated by a couple of attributes. These attributes are typically the speed of the object, right? People who are running particularly fast, or vehicles that are moving very fast, or things like that. So this is one type of anomalies that's fairly common. Unusual human pose. So when people do unusual things, they usually have their bodies usually in an unusual pose. And so this is quite indicative of some unusual activity. So unusual human pose is often quite indicative of anomaly. And there's other things which are not covered by one of these two attributes, which are also anomalous. But these two attributes together already maybe find maybe 80% of the anomalies. So the idea is to construct an attribute-based representation in which we represent each one of these attributes using some deep learning technique. One of them, for example, is very good at extracting object velocity, and another one is very good at extracting human pose. And so this way we parameterize each one of these attributes using some representation. The important thing is that our representation is already split into human interpretable attributes, right? We have the part of it which is correlated to human pose, and we have this other part of it which is correlated to the object velocity. And so then, if we perform k-nearest neighbors on a representation like this, then we can easily find out which one of the attributes had an anomalous value. And using that, we have some understanding of which, we have some level of understanding of why the computer thinks that this new video frame is actually anomalous, right? So now we have an explanation for each anomaly that we detect. Yes, please.
That's a case where you know in advance like what types of anomalies you affect. But if you have no idea at all like what you're affecting, then this form.
Okay, so this is a somewhat subtle point. We don't know what anomalies look like, but what we know is what attributes are relevant for detecting anomalies. So this is one sort of supervision setting that we think is relevant in some cases, not in every case. For the most of the blue ocean anomalies, this will not be sufficient. But this might be sufficient when we have a general indication of what attributes we think are the most relevant for detecting anomalies. But this isn't relevant for every type of anomaly, which actually brings me to the next slide, which is that we also want to have a residual term which takes all the other anomalies, things that we can't explain, but we still want to detect because we don't want to miss out on them. So we have a deep residual term, which is basically summarizing, which gives us some sort of deep representation of the frame, which is not interpretable. We don't understand this representation. We know that it's taken from a deep neural network, which is very powerful. Specifically, we used the image encoder of CLIP. But we can't actually explain why, for example, this representation would have an unusual value, right? We have no understanding of that. And so basically the way that we see sort of interpretable anomaly detection working is like this. We basically want to have one part of the representation which is attribute-based and basically takes in our best guesses of which attributes are most likely to be important for detecting anomalies. And additionally, we also want to have this residual term that is going to take everything else, all the others. Now, obviously, we would love this residual term to be as small as possible and the interpretable part to be as large as possible, but this is basically the tension between interpretability and accuracy. And so this is basically the paradigm that we see as the way of making these sort of representation-based, density-based anomaly detection methods also being interpretable, but still remaining accurate. And I think this is never going to be perfectly interpretable, and it's never going to be perfectly accurate, but this is a way of navigating this trade-off.
And that's what I'm saying. Isn't this introduce like a bias towards the attributes you guessed in begin with? You're going to detect the text. So now it needs to have something to do with these attributes.
So it depends exactly on how you do it. The way that we do it is that we basically perform anomaly detection on each one of the attributes individually. So on the pose attribute individually, on the velocity attribute individually, and on the residual term individually. And then we get anomaly triggers from each one of them. Now, and then in the end, we do combine these different scores into a general anomaly score. So do we have a bias towards the things that we think are more relevant? Yes, but you have to have some priors in order to make progress. But we're not exclusively relying on it. Now, the more you believe in these sort of relevant attributes that you indicated, the higher weight that you would give them, and the less you believe in them, the more weight you would give to the residual terms. But at the end of the day, if you want to make progress, you need to have some prior about the world. Okay, so in video anomaly detection, this, at least surprisingly to us, this is currently the state of the art in video anomaly detection. Now, I don't know if video anomaly detection is something that anyone here is particularly interested in, but I think the general way of attribute-based representations, I think, is something which would be very important in any field. And if we have attribute-based representations, then we would have interpretability. And so basically the way to make sure that we can perform this is by being able to come up with automatic ways of classifying images into a set of important attributes. And this is an active research topic about how can we take an image and basically automatically classify each one of its attributes, because at the end of the day we may want a very large number of attributes in order to get a sufficiently detailed representation. And this is work in progress. Because in video we just had 2, but maybe for some exploratory task that we would be considering, maybe we would want 1,000 different attributes. How can we get this attribute-based representation when we have so many attributes in an automatic, feasible way? So this is something we're looking at. Okay, I'm just going to show this slide, but not going to talk too much about guidance because I don't have time. But I think the main one more point is that anomaly detection is obviously ambiguous. It depends a lot on our objective. For example, if we take a look at this image, we could ask who is anomalous here, and I think the answer is everyone is anomalous or everyone is normal here, right? Because every one of these people has some sort of feature which makes them, or at least a combination of features, which makes them unique, right? So if we ask the computer which one of these people would be anomalous, it might come up with some specific answer, but it is probably quite unlikely to be the one that the operator had in mind. And this is because it really depends on what attributes we consider to be the important ones. And so the question is, how can we indicate to the computer which attributes we consider as the most important? So in the previous section, we described one way of indicating which attributes are the most relevant. However, we've done some work that I'm not going to go into, which is basically trying to indicate which attributes we believe to be irrelevant, right? Because in some cases we might not know which attribute is going to be the important one for discovering the anomaly, and maybe there are many important attributes for discovering the anomaly. But we may know which attribute is unimportant for discovering the anomaly. For example, we may consider sort of device noise to be unimportant for discovering the anomaly, and we would not want to detect things that were different in the attribute of device noise. Or in some industrial settings, we may not want some sensitive attributes to be used, like for example, gender. We may consider that to be irrelevant for anomaly detection. So we may want to exclude some attributes from our anomaly detection, from our representation for the anomaly detection method. And we basically have an approach which removes these attributes from the representation. I don't actually have time to get into the technical parts of this approach. I should just though mention the goals of the technical approach. The goal is basically to come up with a representation which has all the information that we initially had in the data sample, apart from the nuisance attribute, the thing that we don't want to be sensitive in, right? So basically, we should be able to predict every single attribute of the original data sample, but we should not, from this representation, we should not be able to predict the value of the nuisance attribute. So again, I'm not going to go into the technical approach of how we perform this. But if you're interested, I'll be happy to send you the references. Okay. So we've gone through 3 different desiderata, which I think are critical for making anomaly detection useful in the general case for scientific discovery. I wanted to still mention a few other sort of practical challenges for anomaly detection to make it even more useful. So the first one is fine-grained anomaly detection. So for example, if we've been in the forest and we saw maybe 100 different varieties of birds, we don't know which one's which, we just saw a lot of different birds, then we see a new bird and we want to ask, is this different or is this similar to birds that we've seen before? Current approaches are going to fail on that, right? This is fine-grained anomaly detection, and the reason is that there are so many factors, irrelevant factors that change in our image of the bird, that we are unlikely to choose the correct one to specify whether this is a new type of bird or not, right? Because the pose is different and the light is different, and the branch that the bird is sitting on is different every time. So this sort of fine-grained anomaly detection, which is often what we want in sort of more fine scientific applications, is very, very challenging for existing anomaly detection approaches. And basically, broadening the range of settings, making anomaly detection methods work on increasingly more fine-grained anomaly detection problems is work in progress. Another challenge is interpretability for the general setting. So we've mentioned one approach for interpretability, but this was the case where we actually knew in advance at least 2 very important relevant attributes for detecting anomalies. How do we do it in the general case? I argue that this is important, but we don't really know how to do it. So this is work in progress. A third issue is guidance. So we've indicated that there are ways for the operator to specify which attributes are nuisance and to try to remove them from the representation, and then perform anomaly detection on a representation which has fewer nuisance factors. But this right now only works on sort of toy problems. It doesn't work well enough on sort of real world problems yet. And this is super important because at the end of the day, we want to use all the knowledge that science has in order to discover better anomalies. And so we have to be able to leverage human knowledge in a better way in order to perform anomaly detection. And so this is another sort of research direction that we are currently following. The fourth one is extending anomaly detection beyond images. So we've worked on that both for time series and for sort of point clouds and a bunch of other sort of different data modalities. But we don't currently have a generic solution which is able to take your favorite data modality, you put all your data in, and then automatically it comes up with the optimal representation, and then it performs density estimation on that, and it gives you, the most interesting anomalies. This is not something that exists right now. And if your data modality is not, for example, images or text or audio, it is probably likely that recent deep learning techniques might be. I mean, it will be more difficult to make deep learning work for you. Although I've definitely seen cases in which it worked, but this is much less automatic, and it takes a lot more work to get it to work. So this is a really important research direction that the field is currently trying to pursue, but this is really difficult. Okay, so just to conclude, anomaly detection is about representations. And we basically presented new representation-based approaches for several important anomaly detection applications. But I think that we've already seen that being able to fit the correct representation to your problem is a mixture between being an art and a science, and it requires both understanding of anomaly detection and understanding your domain. So generally what we found is that to be able to make anomaly detection work in fields that we don't actually know, in different scientific fields, we found that it was necessary to actually collaborate with domain experts in these fields, because you actually have to understand the domain to come up with the best representation, even with deep learning. And finally, I think that we've seen that there are still many conceptual and practical challenges remaining, but I do want to maybe emphasize that current techniques are already useful, and I think one should consider whether current techniques are sufficient for their domain, because I think in many cases just taking current techniques off the shelf, one can make really good progress on their domain. But obviously things will get better as the field makes more progress. So I wanted to give credit to the students that worked on this. So Niv Cohen, Tal Reis, Jonathan Kahana, Liron Bergman, Ron Abutbul, trying to think if I'm forgetting anyone. And Eliyahu Horowitz. Yeah, so I want to give them credit. And just one thing I wanted to mention that we had, and I think we still have a poster here, on using some variety of the representation of removing nuisance. Basically, I briefly highlighted the task of removing nuisance factors of variation from the representation. So we've actually worked on that. We've collaborated with, so we've collaborated with Zoe and with Zoe Piran and with Mor Nitzan to use that in order to perform some really cool analysis in sort of single cell data. So if you're interested in that, please see the poster, please speak to Zoe. So I just wanted to remind that this poster is around. So that's it. That's what I had for today. If you have any questions, I think now I'm out of time. But I'm going to be here in the coffee break, so if you want to chat, I'll be happy to do that. And beyond that, Niv is going to speak after the break, is going to give you a practical session of how to actually get these anomaly detection methods to work in your Google Colab. So one, please bring your own laptop, because this will be an actual practical session. And two, if you can think of a scientific data set that you want to try whether you can find some interesting anomalies, perhaps from your own research, this might be really cool. So thank you very much.
Some general questions we can take a look. I'm allowing myself to ask the question.
Okay.
So, I mean, we talked during the school about foundation model and how they change the way we go about them. And part of, if I understand correctly, part of the success of foundation models is about getting representation of, for example, language and so on. Yet you're very here. Your anomaly detection is very image based, and what would take to say, for example, read the text and say this sentence really doesn't make sense, or is really crazy in the context of that text? Is it totally different model, or just adjusting the current, I don't know, GPT-3 for the techniques you mentioned here?
So I think these things should work with virtually no adjustment in text. I think the main issue is that we don't actually have good anomaly detection data sets in natural language processing at the moment. That community, for some reason, is not too interested in anomaly detection. And so that's the reason why the field, at least in machine learning, of anomaly detection is mainly working on images. It's not anything too inherent in images. Other fields that have good foundation models, such as text or such as audio, I've actually used the foundation model to do anomaly detection in audio in order to find sort of basic language units. So I know that it works. This is work with sort of Svea Fuchs and Yossi Geshet. But we've actually done work on that on audio. In text, so I basically had a student that was trying to do a project like that, and then they basically didn't complete the project. So I can't guarantee that there will be successful results, but I'm pretty optimistic. And we have some results in some biological field that I don't know if I'm allowed to mention yet, so I'm not mentioning, but something that is very different, that is more similar to language than it is to images. So the main message is this should work on your favorite. I think if you have good foundation models in the data domain that you care about, then I would be reasonably optimistic that these techniques should work.
So in the context of health records, you're saying get your foundation models in order, and then you can detect funny things that are not supposed to be there.
How about the DNA sequence around?
Yeah, so the thing that I'm not allowed to mention is pretty close to that.
Because that seems to me where the anomaly issues are central to health and dishealth.
Yeah, so I'm hoping that we'll be able to release something soon in that space. Yeah, I think that's super promising. I think this is something that
will crush you.
I don't know about that.
It's another application in some sense where you're to try to find that anomaly in a circulating DNA.
Yeah, but again,
the foundation models there are pretty good.
Yeah. Yeah, so but that's generally, I think the main message that I want you to take from this is, look, anomaly detection by itself, I mean, we just do k-nearest neighbors. It's as simple as it gets. Niv is going to show you in the Google Colab how to do it. He'll give you the code. If he wouldn't give you the code, you can program it yourself. This is super easy, but he will do it. This is super simple. This is as easy as it gets. The main issue is to come up with a good representation. In a zero-order approximation, if you take your favorite foundation model and you do a little bit of massaging, not too much, it's probably going, in some cases, obviously not in every case, but in some cases this will give you pretty good things. Obviously, if you try to be a little bit cleverer about it, you can get better results, but I think usually the zeroth order stuff is the most interesting stuff, and this isn't hard to do. I think everyone here can actually do it on their own.
I comment. It feels that if you're going to use nearest neighbours to detect anomalies, I suggest that another important aspect of the representation is that you get independent kind of axes. Because if I'm putting down a metric to detect nearest neighbours, so for example, if the data sits on a manifold within your, say, k-dimensional embedded representation, then nearest neighbours won't work, because you could have an anomaly that's just off manifold, but in terms of the distance, it doesn't look any different. And actually, very early on in your slides, I saw that spiral, I think.
Yes.
Where you had the anomalies, they're actually sitting off the spiral, which is a one-dimensional embedding in a two-dimensional space. And just to note, there's a really interesting, I think, method that can help here, is that there was a recent result that shows if you have points that are not on a manifold, so they fill a space, a k-dimensional space, then the ratio of the distance to the third nearest neighbour to the second, so I take a point, I calculate its distance to its first nearest neighbour, I calculate its distance to its second nearest neighbour, yeah, I look at the ratio of that distance, that's between 0 and 1, I do that for all points. That distribution has a Pareto distribution, a power law distribution under the hypothesis that the points fill the space. And so it might be a kind of an interesting way, first of all, think about how can I try and learn representations that are independent. And then you can use this kind of Pareto test to say, yeah, am I kind of in a cloud?
That's interesting, because basically I think what we're trying to say is, look, if you have a good representation, then the issues that you mentioned might be less severe, because the representation already doesn't suffer from the issues that you mentioned. But we're not guaranteeing that the representation that we have will do it. We're just saying if we chose a good representation, then things will work. But what you're suggesting is there might be automatic ways of testing for that. I think that might be. I mean, that sounds super interesting.
A feature of your representations would be try and represent like different axes which are independent if you're going to use nearest neighbour.
Yeah, so one very common thing that is done in this field is basically to compute the Mahalanobis distance, which at least tries to remove some level of correlations. And Niv, I think, will also show that in his collab. But this obviously only removes some level of correlations, but not the more complex ones that you mentioned. Yeah, I mean, obviously this field puts a lot of emphasis on doing good representation learning, and it's a big field. I mean, it's definitely not us who are going to solve everything in it. It's a big field.
So thank you very much.